ฟังดีจิ้มเร็วทั้งวันเลยโอเคนะเดี๋ยวชวนกันเวที
Hello everyone, can you hear me?
Yes, we do.
Can you hear? Okay, I'm having trouble connecting to my digital pen, so I just have to go use whatever I have. Okay, thank you. All right, let me. You guys already take attendance kah? Sudah, huh? Stop sharing. So I begin now, yeah? Not so many people turn up. Excuse my cat, very, very noisy. Okie dokie, let me see. It's been a while. Okay, let me see what window. Okay, share. Can you see the slide now? Okay, good. Thank you for responding. Okay, so not too sure why I cannot put it into big screen. Ooh, let me see. Let me see. Okay, I think you can see this, right? Hey, it's gone. You can see my still. Okay, I think I'm still sharing. Good. I think so. Okay, how to make this big? Too big. View. Enter full screen. Okay. All right. Okay. Since I enter full screen, so you may need to use your mic to respond to me. Can you see?
Yes, madam. They say some students need your approval.
Sorry?
Some students are still waiting outside the waiting room.
Aduh, ya ke? Ayah. Why? Why I need to enter, let them in? Aduh. You mean in MS Team?
Because I see the comment.
Need approval? Aduh, mengapakah? Why? Accept all. Couldn't update. Why? Are they in now? Okay, where are they? Are you guys still there?
I can see.
Okay, I think I already accepted everyone. I don't see any more. Okay. Okay. So you can still see my slide, right? Okay, I think so. No one is X. Okay, I'm just gonna start into full screen. Okay, so wait, I think I need to record this. It's recording. It's recording. Okay. Okay, let's begin. Okay, so I'm entering full screen, so I cannot see the chat. Yeah, so if you want to say anything, say so. I'm gonna begin now. This is what we have done for modeling with differential equation. I hope you have gone through lecture with Dr. Sarah this morning. So she has gone through discrete probabilistic model. So in your test this Thursday, there will be one question for DPM, yeah? Discrete probabilistic modeling. And then the other two questions will be on modeling with differential equations. Yeah. So basically, what you see here. So there will be two questions coming from this big learning unit. Yeah. So obviously, I would want to see how do you formulate problem into compartmental. Okay. All right.
So we are having 3 questions on it, right? Or
Yeah, three questions.
total, Sarah told us that this morning that there's 4 questions.
4 questions? No.
Okay, so only 3 questions.
Yeah.
All right.
3 questions only. Yeah. 3 questions. Okay, so 1 question from her, and I mean 1 question from discrete probabilistic modeling, and then 2 questions from this one, modeling with differential equations. So basically, I want to see that you are able to formulate the problem into compartmental models, and then after that, of course, the analysis, yeah, on the equations that you obtain. All right. So we have gone through this. You have gone through all the coming up with the compartmental diagram, and then word equations, and going through exponential decay, what it means by continuous and discrete models. In single population, we look at it is exponential growth. Yeah. So there's exponential decay. In exponential decay, we were looking at dating problem. Remember, radiocarbon decaying. In exponential growth, this part, we were looking at the single population. And then we did talk about a little bit on lake pollution models and so on. But the lake pollution, you have already gone through that in your PBL, well, sort of, yeah, in PBL 1, where you were using similar in the alcohol, yeah. But of course, you can model any problem using compartmental models, including interacting populations. So you have seen that as well. We have gone through 4 case studies whereby the compartmental models, the diagrams that you will have 2 compartments indicating there are 2 populations interacting. Yeah, so you have already seen that. So today we are going to look further into the analysis of differential equations. And in fact, since all of you have already set for a differential equation course, it is actually already covered. However, I'm going to go a bit more so that you can see some analysis on the models that we have already formulated last week, and trying to answer through using phase plane analysis, yeah, or in differential equation course, you saw it as phase portrait. It's the same thing actually, yeah. So the lecture is actually, the objective is to understand further equilibrium solutions and to draw phase plane diagrams or phase portrait, and understand what does this diagram means. Yeah, so basically to analyze the behavior of the solutions. All right. So numerical solutions, earlier you have seen how to code. Okay, I've given you some codes, and you can try that out. And you saw that you will need to give values to the initial conditions as well as the combination of parameters. Yeah, remember, we need to give the values for the initial condition and the parameters that you introduce in your formulation, right? So you need to give values so that your numerical solutions can give you the plots, yeah. So, and therefore different combination or different sets of these parameter values will give you another set of solutions. So therefore it is infinitely many solutions. So therefore it's quite difficult to really know whether the behavior of the solution will always be like that, because at the moment you have so many solutions. Yeah, so therefore you will need to have a tool to see the overall behavior of the solutions. Hence, we use the tool that I meant here is actually the phase plane analysis. Yeah, so in phase plane analysis, what you need to do is actually find the equilibrium solutions. You know already how to find equilibrium solutions, and then use these solutions to draw your phase plane. Okay, so basically you will need to eliminate time, because in phase plane you are looking at your unknowns. Yeah, so remember we are talking about two compartments now, right? So each compartment will give you one unknown, right? So two populations. So when you eliminate time, meaning to say you will have in your phase in your plane to be these two unknowns. One will be on the y-axis and the other one is on the x-axis. So there's no time in there. Okay, so you will need to eliminate time. Okay, so what do I mean by that? So say, for example, this is a very simple coupled first order differential equations, and it's linear. Yeah, it's linear. So you have dy dt equals to y and dy dt equals to minus x. It's coupled because you have x and y in each equation, right? And for this case, it's linear, all right? So find the equilibrium points of this coupled system of differential equation. Obviously, for equilibrium points, all you need to do is to, what do you call that? Let dx dt equals to 0 and dy dt equals to 0, right? That's how you find equilibrium points, because the derivative must be equals to 0, right? So when you let dx dt equals to 0 and dy dt equals to 0, hence you only have one equilibrium solution or equilibrium points. That's simply 0, 0, right? Okay? All good? I cannot write it down, you see, because my pen doesn't work. Sorry about that. Okay, so you'll just let dx dt equals to 0, dy dt equals to 0. So then, therefore, you will have one equilibrium point, 0, 0. Okay, so then what you do, you create a axis like this. So your 0, 0 is in the middle here. You can see my cursor, right? Okay.
Yes.
All right. So here in the middle here is your 0, 0. That is your equilibrium solution or equilibrium point. So then you create this two lines. Basically, that's the axis. Okay. And each of the region, you can name it. So I'll start with the first quadrant here as 1, and then going anti-clockwise 2, 3, and 4. So we will have 4 quadrants when you put in your axis. Yeah. So the aim is to find the trajectories. Okay, you find the trajectories using the differential equations just now. Yeah, this one. So what you do is that you consider each region. So say in region 1. Okay, so in region 1, notice that x is greater than 0 and y is greater than 0. Yeah. In region 1, x is greater than 0 and y is greater than 0, right? So if you go back here, so that means that dx dt is greater than 0 because y is greater than 0. So when dx dt is greater than 0, that means x is increasing. Okay? I need to use the pen lah. Let's see. It's very crude. Okay. So I cannot Okay, so in here, x, my God, x is greater than 0 and y is greater than 0. Yeah, my goodness, it's bad. Okay, so that means that the x dt, I hate this. So the x dt is, because the x dt, the x dt is y and y is greater than 0, that makes the x dt is greater than 0. And the x dt greater than 0, that means x is increasing. I cannot write in increasing. Okay, increasing. Okay, x is increasing, meaning to say it's going that way because x is increasing, right? And then dy dt is less than 0. dy dt is less than 0 because x is greater than 0, but then this one is negative. So therefore dy dt is less than 0. dy dt is less than 0 for this quadrant, yeah? In this quadrant. In this quadrant, dy dt is less than 0. That means x is decreasing. Y is decreasing. Okay? dy dt is less than 0, so therefore y is decreasing. All right, so decreasing, that means it's going this way. All right, so since it is going that way, from here go that way, hence the trajectory is moving this way. Paham? This is for first quadrant. Okay, so second quadrant, you can do the same thing. In second quadrant, okay, region 2, y is positive. So here y is positive. That means your dx dt is still increasing, right? Because, yeah, the x dt is y. So y is positive. So x is increasing. X and increasing is this way. Increasing is this way. X is increasing. It's going that way, right? And then, yeah. And then in here, x, in this region, x is negative, right? In this region. Negative. So negative, x is negative. Negative, negative, positive. So dy dt is positive for this region. Okay, it's positive. So therefore, y is increasing. So it's going that way. Okay, so therefore the trajectory is going this way. Boleh kah? So you can do the same thing for 3 and 4, all region, yeah? Okay, so can do that very quickly. I think it's in the next slide. Oh, tada. Oh, tada. Okay, tapa. All right, so we can do that very quickly here. Both x is negative here, and then y is also negative. Yeah, so that means the x, dx dt, dx dt is y. Dx dt is y, so it's negative. Okay. So the x dt is negative, therefore x is decreasing. Okay. X is decreasing. Yeah. And then y, dy dt is negative x, x is negative, so dy dt is increasing. Okay, so that means y is increasing. Increase. So hence the trajectory is this way. This is the trajectory. So, and then, okay, now this is x is, here is x is positive, y is negative. Yeah, so the x dt is x, so x is negative, therefore x is decreasing this way. And then dy dt is negative x, so it's negative. Okay, dy dt is negative. So negative means y is decreasing. Yeah. So hence the trajectory is this way. So when you look at the trajectory, use green, so you can see that the trajectory is clockwise. Yeah, it's clockwise. You see that? Okay, so it's clockwise. So therefore, the solutions will be, you know, it's like increasing in x, decreasing in y, and then decreasing in x, increasing in y. So it is an oscillatory. It's oscillations. Okay, because when you draw, because this one is x and y, it's between x and y, but when you put that in against t, yeah, and this is your x, for example. So you say you start from, let me use black now. So say for example, you start from here, and then you have to move it down, yeah, because it's clockwise. So you see that, okay, I start from x is this side, x, okay, x is first it's increasing because you are moving this way, right? Increasing in x, so you increase. Basically you are you increase, okay, you increase, and then you reach a maximum here. In here you will reach a maximum here, and then you go down, you will decrease in x, okay, in x. So you go down until you reach 0. Yeah, because if you were to go, I make a new line. Okay, you go down and then you will reach x equals to 0 here, right? So that means this one, I cannot sambung lah. Go down and then it will reach 0. You see? And then it's negative x. Yeah, now it's negative x here, and then you go up, then you will reach another amplitude. Okay, another amplitude, and then you go up again. So it's an oscillation. Okay, same thing with y. So you can do also with y, because you can draw y as well. And you start off with wherever you want to start. Say the same thing. If you say y starts here, and you still go down. Yeah, so your y is also, but of a different value perhaps. It's going this for y, it straight away go down, right? So it doesn't go. So sorry about this. So you start with y and then you go down straight. You don't have this thing going up, because in here you start with y and then it straight away decrease in y. Y is here, right? So you are decrease, and then yeah, and then when you reach a value where you go down until 0, right? Go down until your y is 0. Yeah, and then after that you have negative in y. Yeah, and so on. So it will go up again. So it's an oscillations for both x and y. All right. So you saw that in phase plane you don't have time, although you can, like I said just now, you can get the t out, basically the behavior. Yeah. But if you want to know exactly whether this curve that you have, is it a closed loop or not, then you will need to find the equation for the green line, yeah, the green curve, yeah. So which means you will need to eliminate time. So to eliminate time, you use chain rule. Okay, so you can start with dy dt. Dy dt is equals to dy dx equals to dx dt. Yeah, because obviously when you cross out the dx, you will get dy dt. Right? So that is chain rule, and you have seen this in your Form 5, in fact. Okay, so this is chain rule. So therefore, you can rearrange it by making dy dx as the subject. Okay, and hence what it means, you divide both sides with dx dt, okay, of this, and then you get this. Yeah, so dy dx is dy dt over dx dt, and hence you use your differential equations. Remember your differential equation, dx dt is y, dy dt is minus x. So dy dt is minus x, dx dt is y. So you just simply substitute, hence you get this equation. And therefore this equation doesn't have t already. Yeah, so it becomes autonomous. Autonomous means you eliminate the independent variable. Okay, so and you can easily solve for you can easily solve this, right? Well, I put this as an exercise because you have already done this, but I will quickly show it to you. So basically, if I can write it, dy y equal minus x. Salah, right? Salah, my God. Sorry. So it's y dy because y go up here and dx go up here. Yeah. So y dy minus x dx, right? Separation variables. And then you integrate that, you get y square over 2 equal minus x square over 2. Yeah, so I rearrange that, I will get y square plus x, sorry my dearest, equal some constant, which is 2, right? Yeah, so you saw that this is actually the equation of a circle. Hence, this green line is actually a closed loop and it is actually a circle. All right, with radius 2. Yeah. Okay. So that's it. That is phase plane. And I've already mentioned this to you. The movement along the trajectory. So you can start at initial values x0, y0. So like I mentioned just now, you can start because when you start at this point, say here. Okay, another color then. Oh, I've used all the colors. Okay, this. So I can start anyway. Here. Oh, it's the same color. Okay, so this point here is x0, y0. Yeah, it's the starting point. And then I can move because it has to be, what do you call that? Anti-clockwise. So you move. And you know that it is a circle. So it has to meet that point. Okay. So you start and then you follow anti-clockwise because that's how the trajectory is. Okay. Yeah, so clockwise. Yeah, sorry, clockwise. So example gives circle, motion is repeated continuously in time. I already shown that. So basic idea of phase plane analysis, you draw a phase plane diagram with trajectory. And you eliminate time to obtain the exact path of the trajectory because, so here when we eliminate time, and then you solve it, you saw that it is circle. Okay, this is a circle equation. Okay. All right. So hence, what can we say about this differential equation that we use phase plane? So this differential equation, what does it shows to us is that it will give us, I mean, the solution will give us oscillations. Okay, as you saw here. Okay, these are oscillations. That means that whatever your parameter values are, whatever your initial value, okay, it will give you oscillations. Okay, because different initial condition will simply give you a different radius of this phase plane diagram. Hence, what it means in the x and y curves, it simply tell you the amplitude is different. Yeah. So yeah, that is how we interpret the phase plane. Okay. So remember what did we do just now? We use we find the equilibrium solution. Okay. Equilibrium solution is here, and then we create the axis where the equilibrium solution is in the middle there, and then you create your regions, and then find out how does this derivative behave and in each region. Okay, and then from there, then you will know your trajectory. Okay. Right. So yeah, so this one just mentioned what I mentioned just now. Initial point approaches equilibrium point, amplitude of the oscillation is reduced. Okay. Right. So now, so that one just now is a very simple differential equations, very simple coupled system. Okay. Let's look at predator-prey. Predator-prey is this is what we have. Remember, we formulated this last week. Okay. So the question we had, you remember, we asked, does the model always predicts oscillations? That's the question. Because in our numerical solutions, we need to give value to all our parameters, which are beta 1, C1, C2, alpha 2. And we need to give the initial conditions for X and Y, right? Then we saw that it is oscillations, and we asked, if we were to change the parameter values or the initial conditions, will it always be oscillations? That's our question. Now, to answer that question, we will need to use phase plane analysis. All right. So we can begin our phase plane analysis for this system. First thing first is to obtain the the equilibrium solution, right? So equilibrium solution, I can rewrite this. I don't like this color. I can rewrite this. I put equal. So X and then beta minus C1 Y. Right? And this the same thing. I can rewrite it. Yeah. So that's easier for me to see. So CX minus alpha. Right? And if we want to find the equilibrium solution, so we let the x dt equals to 0. So that means this is equals to 0. And dy dt equals to 0. So straight away, you can see that there are two equilibrium solutions. Yeah, one is x equals to 0, y equals to 0. And the other one is y equals to beta over c 1 and x equals to alpha 2 over c2. Yeah, so 2 equilibrium solutions. Now with 2 equilibrium solutions, hence you have your, so first one is here, that's your region, and then the other one, this one is in here, because we say that all the parameters are positive. Okay, so and populations X and Y, they must be positive, hence you are looking at here, right? And with the second equilibrium solution, you will need to create your this vertical and horizontal line. Yeah, so then you create your regions. So you have region 1, region 2, region 3, region 4. Okay, so in region 1, your X, in region 1, X is greater than alpha over C2. Okay, and Y is above here, right? Because we are talking about region 1. Y is greater than beta 1 over T1. You see that? In region 2, your X is less than alpha over C2. But Y is still greater than beta over C1. Yeah, so you see that, right? Okay, so then let's look at region 1 first. Yeah, so region 1, X is greater than alpha over C2. So that means C2X is greater than alpha. So C2X is greater than alpha. So this one is greater than alpha. That means that this is positive because Cx is greater than alpha. So it's positive, and Y is positive because population has to be positive, right? So that means dy dt is positive. So dy dt is positive in this region. Dy dt is positive, so Y is increase. Okay. Cy is greater than beta. Cy is greater than beta. So Cy is greater than beta. That means that this is negative. Okay. And X is positive. So since the one in the bracket is negative, so dx dt is negative. Dx dt is negative. That means X is decreasing. So decreasing. So how does the trajectory look like? Trajectory will look like this. Do you see? Okay, huh? So I do not want to go through all the regions. Okay, and this one is telling you exactly what it is. Yeah. Is just saying that okay. Talking about null lines, this one, there are 2 lines here because we are doing here. So you have X equals to 0 as one line, Y equals to beta over C as another line. These are called the null lines. So from this, you have 2 null lines, and you need to make sure that 2 lines cuts these 2 lines here. That's what it means here, right? Okay, here. Okay. So the equilibrium points occur where the pair L0 and L1 intersect with L2, L3. Okay, those two lines that came, L0, L1 came from the XDT, L2 and L3 come from DYDT. Okay, so that's how you basically find the equilibrium solution. All right, so the one I mentioned just now, so it has been done for you, the region 1, 2, 3, and so on. You try to do it yourself first, and then compare it on the slide. Yeah. So this I already show you basically for region 1. Yeah. Hence, you should get this. Okay. So for each region, you find out the trajectory. Right. So from here, you'll see that it is again a circle. Well, it's not. We don't know whether it's circle or not. Yeah, because you haven't done the chain analysis just now, right? But you know that it is anti-clockwise for this one. So it's anti-clockwise, so you already know that it is oscillations. So the answer to our question, whether it will always be oscillations, so the answer yes, it is. Okay. So path shows that it can either be closed, curves, or spirals. So why I say it can be open, because we don't know whether it's closed or not, right? Until you do the analysis. So you can use chain rule, like how we did just now, to explicitly find y equals to x. Y of x. Okay, and you want to see whether it is a closed curve or not. Okay, closed, then you can fix x to be constant. Yeah, and if the curve is closed, then you can only have at most 2 intersection points. What do we mean by that? Because if you let x to be constant, that means you x is constant, means there's one x here, just one. Okay, so if it is close, then you will have close, right? Close, close, close. Yeah. So you will have only 2 points that cuts through the green line. 2 points. Yeah, here and here. Right? However, so if you show that when x is constant and you obtain y to be two values, that means it's close circle. Well, it's not circle, it's close a curve. Okay, because if it is not close, that means you have cut 1, cut 2, cut 3, cut 4. Okay, so this is spiral, and you have more than 2 values of y. Here, here, and here, here. Yeah. Okay, I think you get what I mean. Yeah. So that's why if you want to show whether it's closed curve, closed, or spiral, then that's how you do it. You just let x to be constant, and then you find out what is y. So if y there are more than 2 y, then it's spiral. If there are only 2 values of y, that means it is closed. Okay. All right. So yeah, we found that already. Enclosing equilibrium point. Tracing the trajectory shows that x, the prey, reach maximum first before the predator. So if you would, that is if you are tracing, yeah. So therefore predator oscillation cycle always lags behind, yeah, the prey, no matter what the parameter values are. Okay, you can use scientific programs such as Skilab to plot the phase plane. So the codes is given here. You can play around with it. Perhaps a different built-in function for the vector field if you are using MATLAB or R and so on. Yeah. So this is how it looked like, the phase plane. Okay. So it is not circle. It's actually an ellipse. But yes, it's close. Yeah, it's close. Right? And it is, yeah, anti-clock. Okay. All right. So you can do that for any differential equations. Okay, any differential equations you can do. So for the case studies that we have gone through last week, so this is a competing species. You can find the equilibrium solutions. So there are actually four equilibrium solutions. Yeah. So remember, because you need to make sure that the null lines are crossing. So hence, for this case, you have 4 equilibrium points. Okay. And yeah, so you have this is from the first one, dy dx, and then this is for the dy dt. That's why you have this. So L0 and L1 has to cut L3 and L2. Yeah, so x equals to 0 and y equals to 0. That's 1. X equals to 0 and that's L0 with L2. So when x equals to 0, then you will get your y. So that's why you have 0 and this one. Okay. And then y equals to 0 with this. So that's why you have this one. And then when L1 with L2, then you will need to do a simultaneous equation to find x and y. Hence, you get this. So you notice you have 4 equilibrium points. And with these 4 equilibrium points, you can actually straight away do analysis because you're talking about the competing species, x and y. So for the first one here, both of them extinct. X and y goes to 0. Yeah. For the second one here, x extinct, y prevails. Yeah. For this one, x prevail and y extinct. And when behold, to answer our question, can they coexist? Yes, they can. So this shows that in competing species, they can coexist depending on their parameter values here, because these equilibrium solutions depends on the parameter values. All right. So yeah, to find the basically the behavior, you will need to have all these different because you have different null lines. Yeah. So you have x equals to 0, y equals to 0 first. So that is x equals to 0 is y-axis, y equals to 0 is x-axis. And then L1 is a straight line. So it depends, and L2 is also a straight line. So it depends on the parameter values which are there, whether L1 is at the bottom of L2 or L2 is at the bottom of L1. Okay, so case 1 is L1 is at the bottom of L2, case L2 is at the bottom of L1. Case 3 is where L1 and L2 cross like this, and then case 4 is crossing as well, but the other side, the other way around. Yeah. So therefore, you will need to find there are 3 regions here. So for case 1, all of them, well, case 1 and case 2 have 3 regions. So 1 here, 1 here, 1 here, and then same thing for case 2, 3 regions. In case 3 and case 4, there are 4 regions. Okay, so then looking at each of those regions and then finding out how the dy dt and dx dt behave according to the region, you will then find your trajectories. So in here, your trajectories are shown already. Okay. So for this case, case 1, no matter where we are, meaning to say what your initial values are, okay, no matter where. So for example, here, this is your initial value, okay, then you will follow the trajectory. So you follow the trajectory, it will go this way, right? So, and if you are down here, this is your initial condition, you also go there this way. So you will see that for case 1, x always go extinct and y prevail. Okay, because it's always go this way, always cut through y axis. Similarly for case 2, no matter where we are, okay, if you are here, you will follow this way. You are here, you will follow this way, and hence you know that for this case 2, x will always prevail and y will always extinct. Okay. Case 3, this is the one that very difficult to find numerically. You will need to like play around with many, but if you know exactly what conditions for alpha, beta, and so on, your parameters, then you will find that because where you start, say for example here, you will go to this point. You go here, you go to this point. Go here, go to this point. And this point is the, that is the point of coexistence. Okay, so the point of coexistence is this point here. Okay, so x, y coexist in case 3. Case 4 depends where you start. If you are here, then you move, and it's either depending on what are your values of your parameters, it will either go here, so which means x extinct, y prevail, or it go down here, y extinct and x prevail. So only in case 3 where it coexists, and you need to really know the range of values of your parameters, okay, in order for you to find that coexistence in competing species. All right. Yeah, so all that I mentioned just now is also mentioned in the slides. And you can do the same for epidemic model and the battle model as well, actually. Yeah, of which I do not cover here. It's just some exercise, but what you will need to know, basically, at least this one is quite, of course, it's quite difficult to do, but at least you will know how to do prey predator, right? So please go through, make sure that you get the same thing, you understand how to get the trajectories. All right, big hint for you guys already. Okay, so basically that is phase plane, and you can use phase plane analysis for any differential equations. So it basically gives you the behavior of the solutions. Yeah, so you will know how does the behavior of your differential equations. Yeah, so that's competing species. So in epidemic model, if you were to do this, then it will tell you what are the what do you call that, how many you need to how many population you need to reduce from the susceptible, so that the spread will not I mean the spreading will not increase. Yeah, so phase plane will answer you for this case. Battle model obviously tells you who will win. Okay, so the epidemic the phase plane will tell you that, and you can go through that. You can use any because the formulation of the models is you have already done, and the way to do it, because it is not so complicated compared to competing species. Yeah, but the steps to do is the same thing. Yeah, first find the equilibrium solutions, and then do the regions, analyze each region. Okay, so yeah, I do not want to spend too much time. I think I've already given you the gist, and like I mentioned that day, I only ask for 1 hour from you for tonight. Yeah, any question? Any question?
All good.
All good. Okay, thank you. Let me, mana tadi? My God, I lost it. All right. Okay. Stop sharing. I think some of you haven't taken your attendance, and I want you to take your own attendance by scanning. Yeah. So let me stop the recording first. Okay, okay. Yeah, for those who have not taken your attendance, please do so. And
can I have my manual attendance, please?
Manual attendance. Is that Benjamin?
It's me, Benedict. Entry number is
Benedict.
82373.
Okay, Benedict. Benedict. 82373. 82373. 82373. 82373. 82373. 82373. 82373. 82373. 82373. 82373. 82373. 82373. 82373. 82373. 82373. 82373. 82373. 82373. 82373. 82373. 82373. 82373. 82373. 82373. 82373. 82373. 82373. 82373. 82373. 82373. 82373. 82373. 82373. 82373. 82373. 82373. 82373. 82373. 82373. 82373. 82373. 82373. 82373. 82373. 82373. 82373. 82373. 82373. 82373. 82373. 82373. 82373. 82373. 82373. 82373. 82373. 82373. 82373. 82373. 82373. 82373. 82373. 82373. 82373. 82373. 82373. 82373. 82373. 82373. 82373. 82373. 82373. 82373. 82373. 82373. 82373
Madam, me too, madam.
Who are you?
You're Amira.
Amira. From? Third year
Yes.
also? Third year?
Yeah.
Nur Amira Amni.
Yeah. Yes. Thank you, madam.
Okay, so for those who have already taken your attendance, you can leave. If you don't have any other question, do you guys have any question? So if none, you can leave. All the best.
Is this included in test 2?
In test 2, okay, very good question. In test 2, yes, a small part. So please read the question carefully, yeah. Read the question carefully. Yeah, so in the question you will be asked first to formulate. So you formulate and then you get your formulation and then read the question carefully and then yes, it does ask you to do some faceplate. So it's within the interacting population question. Okay, so like I mentioned just now, 3 questions, right? Total. So 1 question from discrete probabilistic modeling, 1 question from one of those before interacting population. So one of it, yeah. So it's just one of the case study we did before interacting, and then the third one is the interacting. So in the interacting, you need to formulate, and then after that, there is a question about faceplate analysis within that question. All right. Okay.
Hi, madam. Can I have manual attendance?
And who might you be?
Nur Afifah binti Azmi, 82787.
Is it first year or third year or
I'm third year.
third year? Am I still sharing my this one? Masih ke? I'm not sure whether I'm sharing the.
No, prof, not sharing anymore.
Not sharing. Alamak.
And unfortunately, the QR code is not valid anymore.
Impossible. Tak boleh lah macam ni. Kejap. I cannot find you guys. Where are you? Let me see. Oh no, so many manual attendance. Janganlah macam ni. Die me. It's 8:50. Oh, patutlah. Alamak. Oh, no wonder. It's 9 already now. Wait ah. Siapa yang ni? Sekejap. Oh, I cannot edit it. Oh. Okay. Let me share the screen. Let me share my screen. Entire screen lah. Easy. Okay. Okay, now I am in. You call out your name, siapa yang ada, please. This is